Hello, today we're gonna work on the ideal rocket equation reiteration, how you normally would get it. So first of all, one might wonder what the equation is even for if you don't know what it is. And essentially it describes the amount of change in velocity you can get with the amount of fuel you've got. So m0 is the rocket mass without fuel, mf is the rocket mass with the fuel entirely loaded, w is the velocity. Why did I say W? VE is the velocity at which the fuel exhaust leaves the rocket. ISP is called specific impulse, is the amount of seconds that 1 kilogram of fuel burned can hold 1 kilogram of any mass. And G0 is just the gravity when you're on the surface of Earth. And after we rederive it, I'm gonna try to find the delta V that's approximately required for getting to the low Earth orbit. Okay, let's start. So first of all, what I'm going to do is I'm going to connect VE with the ISP G0. So what we're going to do, we're going to review the way you would normally define ISP, the specific impulse. So first of all, let's define another type of specific impulse. Let's denote this GSP, and essentially that's going to be the momentum produced by burning 1 kilogram of fuel. Now we can define it in a few ways. First we've got just kilogram times VE. That's because if we look into the conservation of momentum and any rocket, then essentially what we have is just an object separating from it at VE, and a certain mass, in this case it's a kilogram. And we have this new momentum here, P1, and do know that, let's label it PF, do know that P1 plus PF is equal to P0 when they were both attached here. According to the conservation of momentum. So when this thing detaches, we need to counterbalance the impulse here so that it still equals to P0. Because if we keep the momentum as it is, this momentum is gonna decrease the total momentum and the conservation momentum wouldn't be true. Alright, now as for this part over here, what I'm gonna do is integrate from 0 to ISP, and what we're gonna have is we're gonna multiply 1 kilogram of mass, so let's just know this kilogram, times G0. That's gonna be the force required to keep it up, and dt, and essentially what we're gonna get is the total amount of impulse required to keep it up. And that's just gonna be kilograms. Okay, G0 is constant, kilograms is constant, so that's gonna be just kilograms times G0 times ISP, and it's also gonna be equal to the other specific impulse that I denote with J. Alright, so what we've got is kilogram times VE is equal to kilogram times G0 times the specific impulse with the time. So we have connected to VE and ISP G0. Very nice indeed. Now what I'm gonna do is I'm gonna find the force that is resultant from all of this ruckus. So force is essentially impulse per type. Well, sort of. In this case, it could be the derivative of impulse with respect to type. And what I'm going to do is I'm going to rephrase this. I'm going to say, this thing tells us the amount of impulse we get from exactly 1 kilogram of burnt fuel. So what we're going to do is we're going to multiply it by the change in mass divided by kilogram. And that's just gonna be the impulse, but we also want to divide it by time. So this thing is dp, and we still have dt here. So what we get is JSP over kilogram times dm over dt. That's just the derivative mass, so let's write it down this way for now, the Newtonian notation. Okay, and now recall this thing over here. So that's just going to be v times derivative of m. And now to find the amount of traveled, let's define time a as time at which m of a is going to be m0, m of 0 is going to be mf. So that's the time by which all of the fuel is depleted. Alright, let's work on that. So VE times derivative of m. That's going to be the force, but we want to find the acceleration, so we just divide that by m dt. Alright, now we can bring out VE out of the integral. And we have, if we lazy thing to integrate, we get m of a, we get m of 0, 1 over dx over x. And what we get is v times the logarithm of x, and when we factor in ma and m0, what we're gonna get is m0 and mf. So recall that when we subtract logarithms with the same base, so we can just plaster it all inside of the logarithm and perform division. So what we get is VE times the initial logarithm of m0 over mf. We already established this relation. So we found delta V, or rather the way to calculate it. Now what we're gonna do is we're gonna find the delta V required for low Earth orbit. First of all, low Earth orbit isn't really far, it's like 100 kilometers away from surface or so, so the gravity can be taken as constant. So here's Earth. I'll draw the orbit a little further away, and that's just for model purposes. So whenever some object has a circular path of motion, that means that the absolute value of velocity is constant, but the velocity isn't. And the thing is, for this to be true, the force has to be applied perpendicular. So here we have velocity, here we have acceleration. So to connect the velocity and acceleration here, what we have to do is we have to express acceleration in terms of velocity. What I'm going to do here is essentially say x of t. Okay, x of t is going to be just the position. Okay, that's going to cause trouble. Let's call it p. P of t is going to be the position or object, and what it's going to be is just r times cosine of omega t, where omega is the frequency of revolution, times x component plus sine omega t times y component. Alright, now when we differentiate this thing once and twice, you can notice that we don't really care about whatever happens in the brackets, because we are just going to bring out the frequency here. And when we take the absolute value, here it's going to be r times omega. Here it's gonna be r times omega squared. So what we're gonna do is we're gonna take the square of the absolute value velocity, so a of t. Then we can divide it. No, wait. Then we can multiply by square root of the radius. That's all it takes to find the velocity. Alright, cool. So the radius of Earth is 6,378 kilometers. If I recall correctly, I may be mistaken here. And then the radius when we talk about low Earth orbit is going to be 100 kilometers more. So V is going to be the square root of A of t, which is going to be just G0 times the square root of 6,478 times 10 to the third power meters. Now, my calculator says that the square root of 6,478 is going to be around 80. So let's approximate it as 80 times 100, so 10 squared. It's going to be 8 kilometers per second. Now, the thing is, that's not going to be the only issue on hand, because recall, that's just the velocity we have to maintain here, but we also need to get here somehow. So, of course, delta V is going to be greater than 8 kilometers per second. Alright, that's it for today. Thank you for watching, and bye.